to another statistical topic. Of course, today our focus is going to be on evaluating goodness of a point estimator. Of course, earlier in the week, we started what I call estimation. And I remember I told you the interest is, on figuring out the true value of a parameter. We do not have resources to study entire elements in the population, and because of that, we are not going to, or let me just say the bad news is we will not be able to get the actual value of a parameter. So what we normally end up getting is what we call an approximate value. Okay, so your estimator we only give you an approximate value because we only work with sample. We acknowledge that from day one in statistics because we're trying to make we're trying to figure out reality, and of course using a model. And the facts remain, a model cannot give us exact reality. There's always going to be an error. And that is the reason why if I want to evaluate the performance of my estimator, if I want to know how good is my estimator, then the analysis will be on the error. The analysis will be on the distance between the estimate you got and the true value of parameter you are trying to figure out. Anywhere, any area where statistics is being applied, we appreciate the fact that our result we're going to get at the end of the day will not be exact, but approximate. Let me quickly remind you of regression analysis. Whether linear regression or non-linear, of course, you're actually going to have, when you specify your model, there's going to be a random part that we call the error. If you want to tell how reliable is your model, if you want to test, okay, if you really want to figure out what I call model evaluation, what you actually going to be doing is what I call residual analysis, which means you are analyzing the error. Of course, they're going to tell you a modeling error is more or less unexplained variation, because it is not everything, it is not all variation in the response variable that your model will explain. We acknowledge the fact that there's going to be error, and that is why every statistical model has assumptions, and assumptions in statistical models centered on the error. So if I really want to know how good is my model, then I need to investigate whether assumptions are met. So today, the focus is going to be, if I use whatever estimator, how can I be sure the estimator is a good one? And that is why this topic is called evaluating goodness of a point estimator. Okay, so on the outline, we're left with something that we didn't do on Wednesday, which is a sample variance as an unbiased estimator. There are two forms of variance, and reason why we settle for sample variance, of course, I'm going to show you that today. Then I'm going to go into error of estimation. Like I said, anywhere in the world where you are actually performing estimation, there's going to be error. We acknowledge the fact there will be error, but we actually want to see if error is minimized, if the distance is not huge, then maybe we may be able to rely on the estimate. Then we're also going to use the idea of normal approximation, then application. Now, let's get started. If there's anyone who doesn't understand at any point in time, please ask question. Now, I want to start with the variance. You know, the other time I told you, we're looking for population parameter. At times, the population parameter could be mean, could be variance, could be standard deviation, okay, and so on like that. And even if your population of interest is average, mean, okay, if you want to tell how reliable is the mean, of course, I'm talking about basic statistics where you compute the sample mean. If you want to tell how reliable is the sample mean, of course, you need variance. Now, if you want to compute the variance, it means we need a formula to compute the variance. So which formula are we going to use? I needed to take a look at this. This particular formula here, okay, that was an estimator that was suggested. There's another one that is going to be 1 over n instead of 1 over n minus 1. Okay, we're actually going to have another one that is just instead of 1 over n minus 1, it's just going to be 1 over n. Then we're going to have summation y high, right, minus y bar all squared. Okay, now why is it that we prefer the one divided by n minus 1 and not the other one in estimation for variance? Okay, is because the sample variance is an unbiased estimator for the true variance. The true variance is this, sigma squared. That is a true variance. That is a population parameter. That's a population variance. That is what we're looking for. Okay, so the reason why we actually prefer to use the sample variance formula divided by minus 1 is because we've been able to prove that expected value of s squared, okay, is equal to sigma squared. Okay, it's equal to sigma squared. And you know what? I'm gonna quickly show you that. Give me 1 second. Okay, it's showing on the screen. What I'm gonna do, I will use a board. I'm also going to, let me see if it works. Okay, I'm gonna see if I can. Let me see if I can have my whiteboard here too, so that I will be able to write. Now, give me 1 second. Okay. Okay, so that makes sense. Now, excuse me. Now, this is the story we got this proposal. And we got another one. Okay. We got another one that is not divided by minus 1. Why is it that this is the one that we prefer? Okay, because we've been able to prove that this is equal to that. And I want to show you the proof right now. I need you to focus on this. I'm going to show you the proof right now. Okay, now the sample variance is 1 over n minus 1 summation. I start from 1 to n, yi minus y bar squared. Now, I'm going to show the expectation. So I'm going to, let's take the expectation of both sides. Okay, 1 over n minus 1 is a constant. 1 over n minus 1 expectation into this. You see that? Now, what I'm going to do, 1 over n minus 1 expectation into, if you expand what you have in there, okay, you're actually going to have summation yi squared minus 2 y bar summation yi plus, okay, because y bar is a constant, then the summation is just going to be n. I'm going to have ny bar squared. Any question on this? Any question? Any question on that? Okay, now if you take a look at what I got now, I'm going to have 1 over n minus 1 expectation summation yi squared. If you take a look at that, summation y. If y bar equals summation y over n, then summation y will be ny bar. Does that make sense? So I'm going to have 2y bar ny bar plus ny bar squared. Well, take a look at this guy. That's a negative 2ny bar squared. Negative 2ny bar squared plus ny bar squared will be minus ny bar squared. Now I'm going to erase this guy now to have more room. Okay. Now if I want to rewrite now, expected value of a squared equal 1 over n into, okay, don't forget we got expectation, so summation yi squared minus ny bar squared. That is what that guy is going to give me. Now the moment I go that, what I'm going to do now, okay, I want the expectation now to attract. I'm going to rewrite this as 1 over n. Summation is going to come out, okay, into expected value of y squared minus expected value of y bar squared. I start from 1 to n. Now, some of you may be wondering, there's a particular n. There's a particular n y bar. Give me 1 second. Let me put this in down. Now, there's a particular n y bar squared, right? That n is the same thing as summation because the y bar squared is a constant. Okay, the y bar squared. Okay, the y bar squared is a constant. So the summation here is the same thing as that n. So I bring it out. So when I bring it out, okay, so when I bring it out, now the next thing that I'm going to clean this guy now. Now I want to work on this and I want to work on that. Remember, What is the variance of y? Expected value of y squared minus expected value of y all squared, right? What is the expected value of y squared now? Because I need that here. There's going to be variance of y plus expected value of y all squared, right? Now, if for this guy, for that second one, expected value of y bar squared now is just going to be variance of y bar plus expectation of y bar. Do you see that? Do you see that? If the variance of y equal to that, if I can write expected value of y squared like that, I can also write expected value of y bar squared like that. Now, this is what we're going to have. What is the variance of y? Sigma squared. What is the expected value of y? Mu, right? It's going to be mu squared because that guy is squared. What is the variance of y bar? That's sigma squared over n, right? Sigma squared over n. What is the expected value of y bar? Mu. So this guy is going to be mu squared. Now, if I want to plug in now, okay, if I want to plug in now, this is what I'm going to do to plug in. So if I want to plug in now, what I'm going to plug in, okay, don't forget what I brought out the other time. We have 1 over n. That was another. Don't forget we have 1 over n minus 1. Okay, so this is 1 over n minus 1. Don't forget, I think I erased that. You remember when we started, we have 1 over n minus 1. So 1 over n minus 1. Okay, now summation. Now that summation is out. It's going to be it's going to turn into n. N into what is the expected value of y squared? I'm going to write sigma squared plus mu squared minus what is the expected value of y bar squared? Sigma squared over n plus mu squared. Okay, so right now, if I clean this guy and I simplify, if I clean this guy and I simplify, okay, so this is n over n minus 1. Of course, you know this the mu square is going to cancel out. That's a negative, right? Then I'm going to be left with sigma square minus sigma square over n, right? Now, if this n should multiply that, that will be n sigma squared minus, okay, n multiplied by that is going to cancel that n, right? I'm going to have sigma squared, then divided by n minus 1, right? So I can factorize sigma square out. When I factorize sigma square out, okay, what am I going to have? Sigma square into n minus 1 divided by n minus 1, which is going to cancel out. What do we have? Sigma squared. So therefore, we've proved that the expected value of sample variance is the same thing as population variance, and that is the reason why we use that to compute variance from the sample. This is being recorded. Okay, this is being recorded. Okay, so I'm going to stop my share right now, and I'm going to go back into the lecture slide. Okay, so I'm going to go back into the lecture slide. Let me see the lecture slide. I'm going to share that. Okay, now, and I want to go, and that is the reason why when you have set of data, okay, when you have a set of data, give me 1 second. Why it's not showing well here? Give me 1 second. gonna stop that now. Yeah, let me see. What is the show? Oh, so that's to show very well here. You're still loading. Oh, give me 1 second. I think I need to. All right, that is. Okay, I think it should work. It should work out now. Okay, now I want to go into error of estimation. Now, by error of estimation, we're just trying to appreciate the fact that there's going to be a distance between estimator and its target. There's always going to be a distance. Okay, so we're going to denote the and that distance. It could be negative. The error could be negative or positive, right? And that is the reason why we are actually using the absolute difference, because it could go the other way, like negative or positive. Now, I want us to apply the knowledge, what we've learned in this class before. I want us to apply the knowledge of Chef inequality. Don't forget, we use Chef inequality when the underlying population is not normal, right? Okay, if it is not normal, Chef rule apply. Okay, when you have normal, okay, the empirical rule apply, right? Okay, we want to use our knowledge of Chef inequality, our knowledge of law of large number, and our knowledge of central limit theorem to be able to place a bound. We want to place a probability bound on the error. We know there's going to be error. You're going to see at the end of the day, what we want to do now is the reason why we're going to have interval estimation. Now, take a look at this guy. For k greater than 0, you've learned that we want to be able to find the probability. We want to be sure that that distance, okay, will not be more than the distance between the estimator and the true value of a parameter. Can we be sure that the distance between them will not be more than a particular threshold? Okay, will not be more down. Because of that, we can actually use the idea of a Chef inequality. Okay, where we're trying to say the probability of the absolute difference between the estimator and the parameter will be less than epsilon. What is the epsilon in this case? The epsilon is going to be k standard deviation of that particular estimator. Okay, why am I? You can see inside the square root, what do you see? Mean square error. Don't forget, because the estimator may be biased or unbiased. You understand? If it's unbiased, the mean square error of the estimator becomes the variance. If it is biased, of course, you have the mean square error. So that greater or equal to 1 minus 1 over k square. So that 1 minus 1 over k square is the probability that the error of the estimation will not be more than k standard deviation. This is the k standard deviation here. This is the k standard deviation here. Do you see that? That is the k standard deviation, the square root of a mean square error. That's a standard deviation. Does that make sense? Now, if we want to go by way of Chebyshev, okay, if k is equal to 2, you remember? If k equal to 2, at least 75%. Because if k equal to 2, you're just going to plug in 2 to wherever you see k. That will be 1 minus 1 over 2 squared. And that will be at least 75%. So what are you using here? You are using the Chebyshev law. That's the Chebyshev rule. Maybe the estimator, okay, you were computing that estimator on a sample that you choose from a distribution that is not normal. Does that make sense? Okay. But what of in a situation now where we have an estimator, it is unbiased, and it is normal. You know what I mean by it is unbiased and normal? Do you know what we mean by unbiased and normal? Okay. The unbiased and normal is like when you look at the distribution of the theta curve, when you draw the histogram, right? It's normal. And it's also unbiased, meaning expected value of theta curve equal to theta. Okay. Now, in that situation, you don't need Chebyshev. Okay. You don't need Chebyshev. What do you need? Empirical rule. Okay. When k equal to 2 in empirical rule, okay, what happened? When k equal to 2 in empirical rule, you know, I told you the other time, 95 point something percent of the observation will lies, right? So which means we can be 95 point something percent sure that the error estimation will actually be bounded by 2 standard deviation of the theta curve. Why am I using standard deviation now? Okay, I'm using standard deviation now because I believe that is the square root of the variance. I believe the moment estimator is unbiased, where I don't need to talk about mean square error. I'm just going to talk about the variance. Now, but what if we know that theta cap is unbiased and approximately normal? There's a difference between these two statements. Please take notes. There's a difference between give me 1 second. There's a difference between this guy and this guy. If you take a look at the first one, you didn't force it to normal. It's normal. You didn't force it. Maybe at any sample size, it is normal. But here, you force it. Maybe this is asymptotically normal. Asymptotically normal means maybe it becomes normal when you take a large sample. Maybe the central limit theorem applies. Does that make sense? Okay, when I'm talking about, and let me tell you this, most of the common unbiased estimator, in fact, the one I show you on Wednesday, they are approximately normal. Initially, they were not, like, look at, for instance, binomial is not symmetric, but it can be normal if the sample size is sufficiently large. And that is why I'm asking you to recall here the common estimators. They are all approximately normal. They were not normal initially. Does that make sense? They were not normal initially. Something was done for them to be normal. If you want to talk about either sample mean, sample proportion, difference of means, difference of proportion, they are all approximately normal. It means, central limit theorem applies when the sample size is large. Okay, take a look at that. Now, if theta cap is approximately normal, but let me tell you this, whether approximately normal or normal, Okay? I'm going to say that again. Whether approximately normal or normal empirical rule applies. Does that make sense? Whether approximately normal or normal empirical rule applies. Now take a look at this. If I have a theta curve that follow normal distribution, it's approximately normal with the mean theta and the variance or sigma squared or theta curve, where that then we can actually boast that the probability within 2 standard deviation will actually be that. And like I said, whether approximately normal or normal empirical rule applies. Okay? So which is what I'm trying to say here. Does that make sense? Now, if theta cap is an unbiased estimator that's approximately normal, then with about 95% probability, the error of estimation will be less than 2 standard error bound. Less than 2 standard error bound is just going to say it's going to be within 2 standard error bound of the theta. Which means if I want to talk about within 3, that will be about 99.75%. Does that make sense? So empirical rule apply for either normal or approximately normal. I want to go into example 8.2, which is a proportion. Okay, a sample of n equal to 1,000 voters randomly selected from a city show that y equal to 560 in favor of a candidate Jones. Estimate P, the fraction of voters in the population favoring Jones, and place a 2 standard error bound on the error of estimation. Take a look at this question. I told you the other time, the P cap is the average. Why is the P cap the average? Because it's when you choose somebody randomly from this city, it's either a voted for John or not. That's a Bernoulli, right? The sum of Bernoulli is sum of y become binomial. When I divide by n, okay, that is going to give me my P cap. Therefore, P cap is the same thing as y bar. Okay, now a sample size of n equal to 1,000 voters. Oh, by central limit theorem, n equal to 1,000 voters, you know the rule of thumb, right? It has at least what, 30, right? Okay, take a look at that. Now, and a sample of n equal to that, y is observed to be that 560, right? 560. 560 is sum of y. If you divide that by 1,000, you're actually going to have maybe 0.5. So the P cap is observed to be 0.56. Does that make sense? Now, we can now impose a central limit theorem because the sample size is large. Then it's going to be approximately normal. You can see by CLT. Why do I say by? The CLT means central limit theorem. Okay, the sample size is large enough to impose a CLT. That I can actually write that my P cap, you know, if you write P cap, if you don't put approximate, you are not totally right. Because initially, the distribution of the population was Bernoulli and binomial, not normal. But when we choose a last sample, it's now approximately normal. Does that make sense? Okay. Now with that, of course, you know the sigma, right? You know the variance is P into 1 minus P over N. That is the variance for the Y bar. Y bar is something as P cap. The variance of Y in Bernoulli is P into 1 minus P, right? But the variance of Y bar, which is sigma square over N, will be P into 1 minus P over N. That's why you have that. Now, they talk about 2 standard deviation, right? 2 standard deviation, right? The sigma P will be the square root of that variance. Okay? Now take a look at that. So what are we trying to say? We need the values of P to be able to compute that. Okay, we can actually use the best guess, the one that we have right now. That was why I said, unfortunately, to calculate that, we need the values of P. Now, but we have the best guess, P cap. We can substitute P cap. Okay, that is what we actually, can you see that? We substitute that. Can you see that? At the end of the day, it gave us this bound. It gave us 0.03. Okay, the 0.03 is the epsilon. Epsilon, that's a bound. That's a probability bound that we just computed. Okay, based on the fact that we have been told we have been given K. K is 2. Okay, now if I now want to, so which means, what do I expect by central limit here? Empirical rule apply. Okay, that will be 95% in probability, but the error bound for that is 0.03. If I want to make a conclusion now, I'm going to say the probability that the error of the estimation is bounded by 0.03. You compute the error bound, right? It's approximately 0.95. Why do you say 0.95? You apply empirical rule for, within 2 standard deviation. Don't forget empirical rule. Okay. Now, thus, we can be reasonably confident that the observed value of P cap is 0.56, is within the 0.03 of P. Take a look at that. In practice, we often report a point estimate within it, the 2 standard error bound. If I now want to report it to, if I want my report to make sense, I can say the fraction of voter in favor of John is estimated to be 0.56 plus or minus 0.03. When you listen to news, when you listen to when CNN, MSNBC, Fox News, and the like make projection in election, they're always going to say within certain margin of error. They always say that. That is acting like a margin, 0.03. The margin of error enables us to know how sample reflects the overall view of the population, how you can rely on your estimates without them. That's why it makes a whole lot of sense presenting your results in an interval. Okay, I want to go to another example. This time around, 2 population. Okay, we want to focus on the difference of means now. Estimate the difference of mean. We know whatever estimator that you actually use, there's always going to be error of estimation. Okay, now for this, now estimate the difference in mean miles to weigh out and place a 2 standard error bound on the error of estimation, where we're focusing on the difference of means. Okay, now the true point estimate is this guy. This is what we're looking for. We can never get that guy. To be able to get that guy, we're going to study everybody in the 2 population. We don't have time for that. But what do we normally do? We estimate then cap with the with means, sample means. Okay, now the sample mean given, by the time you subtract, that's a point estimate. That point estimate could be wrong or right. Okay, now because these are very large enough, the sample choosing are very large enough, N1, N2 equal to 100 tires, we can impose the central limit theorem. And this is going to be the standard deviation. I gave you this guy the other time. Okay, and in the end, if I want to compute now, which means what I'm actually seeking for is this. This is the error bound that I'm seeking for. The error bound is going to be the absolute value between the difference of the estimator and the true difference. Okay, then I want to, then the epsilon now, my epsilon is going to be 2 multiplied by the standard deviation of the difference, which is this guy. Plugging that in, what do we have? We got that guy out. Okay, we just figure out the error margin now. Now, conclusion, we can estimate the difference in mean mile to weigh out to be that, to be 1,300. The 1,300, the difference is that will be the point estimate that we for us got. But what about the error margin? The error margin is what we calculate. And we expect the error of estimation to be less than, okay, with a probability of 0.95. Where is the probability of 0.95 coming from? Because they mentioned 2 standard deviation. And don't forget, empirical rule apply because of the fact this is an approximately normal. Okay, 2 standard deviation is 95%. So that we can estimate that the difference in the mean miles to be, so that's going to be the point estimate of the difference plus or minus the margin, where we're going to subtract that, we're going to add that, which means we consider the error to the left and the error to the right. Now, do you now see the origin of interval estimation now? We have interval estimation because we're placing a probability, bound error, okay, on the difference between the estimator and the true value. You can see statistics is very, very interesting. Very interesting when you follow what is behind the scene. Okay, when you follow what is behind the scene, like, what am I doing? Oh, we're placing a bound. Oh, we're placing a bound. We know there's going to be difference, right? And if there's going to be difference, the difference shouldn't be more than. You know what I mean? Because the moment the difference is more than that, then we're not going to accept that. That estimator is not going to do a great job. Is there any question today? You're going to see in the error of estimation that we did today, we've applied the knowledge of central limit theorem. We also use Chebyshev inequality. The idea of Chebyshev coming in when we realize that maybe the central limit theorem does not apply. Okay, the central limit theorem does not apply, and maybe we just want to do so. At times we could decide to say, okay, let's see by central limit theorem what happened. By central limit theorem what happened. But there's something I wanted to take notes. An estimator could be biased. Okay, an estimator could be biased, and it may be unbiased. When an estimator is unbiased, it could follow normal distribution. It may not follow normal distribution. It doesn't matter. The only thing we're going to, if I want to figure out, since I know using Chebyshev, I need a K standard deviation. Then if I'm referring to bias estimator, okay, the standard deviation of the estimator will be the square root of the mean square error of the estimator. Please take notes. Of course, if I'm dealing with the unbiased, then I can use variance, the square root of the variance. So the t-test, the confidence interval, the t-test that we're applying in statistics, we're doing that under the assumption that it's either the population you are choosing, the sample is is normal, or you are choosing a large sample. And that is why most of the statistical tests have assumptions of normality. The normality we're talking about may be, the population may be normal at the beginning. If the population is normal, irrespective of the sample size, the sample statistic compute from that will be normal. I'm going to say that again. Quote me. Anywhere in the world, if the population you are choosing from is normal, whatever sample statistic you compute, whether you take a sample size, where your sample size is small or large or whatever, is still going to be normal. But if your population is not normal, if you want to achieve normality for your sample statistic, then you have to take a large sample. That is a requirement of central limit theorem. I enjoy statistical movie a lot. You know why? It's a movie. And make sure you don't miss any scene in the movie. When a movie is very interesting, and maybe you are watching a movie and there's a kind of distraction, or somebody was knocking on your door. If you are watching a statistical movie and somebody knocking on your door, why can't you skip the movie, like pause it? Because every scene is very, very important. They are connected. The moment you don't get that story, it will be difficult for you to be able to connect. This is the end of the last, how many weeks now? This is 4th week. Oh my God. The what is it called? The midterm is very close. Okay. I'll check the syllabus and I'm gonna say on Friday, the next Friday, I'm not gonna be here in person. I actually have a conference to attend. You know, the next Friday, October 6th, you can only join my Zoom for lecture. I mean Friday. Does that make sense? I'm gonna put but next Monday, Wednesday, of course, I'm gonna be here. But Friday, you're going to attend my lecture by joining Zoom. The link to the Zoom is on the canvas. And of course, you don't need to come here on Friday next week. Make sure you all, oh, go ahead. Exactly. I'm going to allow a cheat sheet, one page, sorry, one sheet, double-sided. You can write on it, you can type. Does that make sense? And I'm also going to allow you to come with a list of distribution. You know, you need it, list of distribution. I will be the one. I'll provide it. Okay, I'll provide it. I'm going to publish that on Canva. That's a good question. Go ahead. Is there going to be what? Oh, a study guide. Actually, a class will be dedicated to practice question. I'm going to release practice exam question before the exam, and I'll just come to this class, discuss about it, tell you about my expectation, then tell you about the study guide as well. Yeah. Okay. See you next week. Stay safe.